Alright, having proven theorem 1, we can now use that for several other theorems. So theorem 2 is the next step. Already taken 50 minutes, so I'll try to speed up the process, otherwise this lecture is going to be very long. So theorem 2 is, theorem 2, it says that, okay, so relatively m and n, so you have two integers that are relatively prime. So if m divs, in other words divides, so if m divs in a, so a is just another integer, then m divs, divides a. Now that's in the abstract. I mean, think about it. Right? You've got a product here of two integers. Now m does not divide n because it's relatively prime, so m does not divide into n. But you're told that m does divide into the whole product. So if n does not divide into n, it must divide into the a. And that just seems common sense. So let's actually prove it. So if that's the case, given that m and n are relatively prime, therefore this m divides the a. So how do you prove that? All right. Now m and n are relatively prime. Okay. So from theorem 1. Because, are you familiar with that symbol for because? Like, therefore, I think it's that way, because it's sort of the opposite. So, therefore, because. Right, so because relatively prime of m and n, that's just a way of saying that m and n are relatively prime. That implies that there is an x and a y belonging to the integers such that ax plus by equals 1. But we haven't got a and b now, we've got m and n. So so I'll put m here and n. Okay? So instead of a and b, so m and n. So we know that mx plus my is 1. Alright? Now the trick is, there's always a trick, multiply through both sides by a, by this letter a. And why do you do that? Well, you'll see in a minute. Okay, so amx plus any equals a. Alright? Now, that's a y. Now, have a look at this. You can divide this number, 3 integers, product of 3 integers, you can divide that number by n, right? Because there's an n, there's a factor. Now, an, or na, m divides na, here it is here. So m divides an. So m divides this and m divides this. So that means that m divides the whole of the left-hand side. Okay? Now if m divides the left-hand side, it must divide the right-hand side, because these two sides are equal. So if m divides that, m divides that. And there it is, there's your result. Okay? So that's theorem 2 proved. So that was a lot quicker, right? So you're also beginning to see the usefulness of theorem 1 with using this. So we used it rather quickly and got it proved. Alright. Right, now theorem 3, it states that, okay, so m and n are relatively prime, so just the same as here. So rel pr m and n. Okay, so you have two integers that have no common factors. M and N, so M and N are relatively prime. Okay, now if, here's the theorem statement, if M divides divs, if M divs K and N divs K, so both M and N divide into K, so if M divs K and N divs K, then, this is what you've got to prove, then the product of M and N, so Mn divs K. Okay, that's what we have to prove. And it's just one way, so if, so that's your statement P, and this is your statement Q. And it's just a one way, so we have to prove if P then Q. Okay, that's what we have to prove. All right, now M, I'll use the same as in the textbook, so if you're studying it. All right, well, let me just start here. Now, N divides K, okay? So N is a factor of K. So you can write K is N times S. S is just some integer, right? So if N divides K, N is a factor of K. So N is a factor of K. So you can write K in this form, okay? I'm just trying to remember here. So therefore, now what about M? Okay. Now you're told M divides K. M divs K. Okay. Now M does not divide N, right? Because M and N are relatively prime. So M divides K. So M divs NS, right? Because that's K. So M divides NS. Now M does not divide N because that's the left-hand side. Well, because you're told M and N are relatively prime. Now from the second theorem, theorem 2, that's this one, if it doesn't divide this one, but it does divide the product, the whole, therefore M divides S. Follow that logic? That's what theorem 2 says. I'll say that again. So M divides the whole thing, right? M divides K. And K is this, NS. Now M does not divide N, but theorem 2 here says, therefore M does divide S. Okay? So that implies M divs, or divides, so M divides S. So that means M is a factor of S. So that implies that you can write S in the following terms. F, S equals M, what do we call it? T, okay? So T's just another, it's an integer. So if M divides S, that means M's a factor of S, okay? So that means you can write S in these terms, that it's M times some other integer. Okay? So M is a factor, okay? So S is MT. Alright, now here's your S here. So just plug in this MT here. So you'll now get K equals N, and the S, so you put MT here, so NMT. Well look, that means that NM is a factor of K. Okay? So if nm, or mn, same thing, if mn or nm is a factor of k, that implies that mn divides k. And there it is, you've proved it, right? So if m divides k and n divides k, then the product of m and n divides k. And here it is proved. Okay, right. So theorems 1, 2, 3, done. Now I'll talk a little bit about prime numbers. Now every science student knows what a prime number is, but for those few of you who have forgotten, a prime number is an integer whose factors are only itself or 1. Okay? In other words, a prime number cannot be divided by other integers except itself and 1. Right? So 5 is a prime number. 9 is not a prime number because you can divide it by 3. You know, there is another integer that you can divide it into by, and that's not 9 or 1. Okay, so that's what a prime number is. So giving you the definition, prime number has no factors, right? No integer factors except itself and 1. All right. Okay, let's do theorem 4.